Again, welcome to Operating System CS332 class. Again, this is Computer System Overview, and we're going to focus on memory hierarchy and relationships. As we know, in every computer system, there are different types of memory, from register, cache, all the way to the main memory, which are discussed the relationships between memory and also their hierarchy. And we know that the design constraints on a computer's memory can be summed up by three questions. And the three questions are how much, how fast, how expensive. And the faster the memory is, the less the amount and more expensive. The slower the memory, that means it will be less expensive and a lot. So we may answer these three questions. So now the question of how much is somewhat an open-ended question. We don't know how much specific value. Now, if the capacity is there, then application would likely be developed to use it. Also, the question of how fast is, in a sense, is more easy to answer, because to achieve the greatest performance, the memory must be able to keep up with the processor. That is, as the processor is executing instructions, we will want also the memory to be providing enough information at a constant rate with the processor. Otherwise, it will reach a stage whereby the processor will pause or stay idle because there's no data information if the memory is slower. So here we say if the capacity is there, application will likely be developed to use it. Now, memory must be able to keep up with the processor. And now the cost of memory must be reasonable in a relationship to the other components. And that was, again, our final question. We need to consider the cost. So for a practical system, the cost of memory, again, must be reasonable in relationship to other components. So this is the concept of memory hierarchy. We're going to consider these three characteristics, or I'll say the three questions of the memory: how much, how fast, and how expensive. So again, memory relationships, we can see here the faster access time equal to what? The greater cost per bit. So if the memory is faster to access by the CPU, then the cost will be higher, as we said earlier. And also the greater capacity goes with the smaller cost per bit. So the higher, the larger the memory, the cost may go down, but the speed may slow down. So here also we say the greater capacity equal to slower access speed. So as might be expected, there's always a trade-off among these three key characteristics of a memory: the capacity, access time, and the cost. And those are the three questions we were asking before. So a variety of technologies are used to implement memory systems. And across this spectrum of technologies, the following relationships hold: faster access time, greater cost per bit; greater capacity, smaller cost per bit; and also greater capacity, slower access speed. So the dilemma here is that we are facing here is very simple or very clear to the designer. The designer would like to use memory technologies that provide for, again, large capacity memory, both because the capacity is needed and also because the cost per bit is low. However, to meet the performance requirement, also the designer needs to use expensive one, relatively lower capacity memory with fast access speed. So I would say the difference between the main memory, which is more larger but slower to access by the processors or CPU, comparing to cache, which is closer to the to the CPU, so faster to access, but very expensive, so it must be less memory. The capacity must be less. So this is our memory hierarchy. Going down the hierarchy, first of all, decreasing cost per bit, then increasing capacity, and then increasing access time, decreasing frequency of the access to the memory by processor. So here we have the inboard memory, then outboard storage, then offline storage, which will be more slower. And also, so from the higher, it's more faster and less capacity and most expensive. So one will be the registers, which are normally, even some of designers have the registers inside the CPU. Caches will be next to the CPU. Then main memory. This is the only place, this is called the inboard memories. The computer of the CPU can only access these three types of memory. Then we have the outboard storage, like again, CD-ROM, the hard drive, etc. But the CPU cannot access any of this. So in order to execute a program or any task, the program and the data must be loaded to the main memory. CPU can access the main memory, but it's very slow. We may discuss this more detail when we start main memory chapter. So as we expected, again, there's always a trade-off among all the three key characteristics: the capacity, the access time, and also the cost. Now, the way out of this dilemma is to not rely on only one single memory component or technology. So we see most of our computer system today, we have all the three types of memory in our computer. We may have a register very inside the CPU, the chip. Then we may have a cache very close to the CPU. Then the main memory a little more far away from the CPU. So a typical hierarchy is, as we saw the illustration, again, from memory, so the down is more slower, which is the magnetic tape. So next, again, we can see the diagram performance of a simple two-level memory. And we have the fraction of access involving only level 1, hit ratio, and also the average access time, T1 to T2, T1 plus 2, all the way. Now, suppose that a processor has access to 2 levels of memory, which again is level 1, containing 1000 bits, and has an access time of 0.1 microsecond. Level 2 contains 100,000 bits, and it has access of 1 microsecond. Now, assuming that if the byte to be decreased is in level 1, then we know the processor accessing it directly. Now, if it is in level 2, then the byte is first transferred to level 1 and then accessed by the processor. So for simplicity, we can ignore the time required for the processor to determine whether the byte is in level 1 or 2. That's the concept here again. Main memory or the data programs are loaded there when we open our program or data. Now for the CPU, we want to transfer the data from the main memory either to the cache, which is next to the CPU, then from there to the register, which is another memory inside the CPU. So register will be holding the data or the program that is being executed during execution time. Now, suppose that the processor have access to 2 levels of memory. As we said, level 1, we have 2, 0 and 1, contain 1000 bytes and has access time of 0.1 microsecond. And also level 2 contains 100,000 bytes and has access time of 1 microsecond. Now, assuming that if a byte to be accessed is in level 1, then the processor also can access it directly. But if it's in level 2, then the byte is first transferred to level 1, then accessed by the process. So here, this diagram shows general shape of a curve that models the situation. We can see that the figure shows average access time to a level 2 memory as a function of heat ratio, which is the H, the heat ratio, where H again is defined as the fraction of all memory access that are found in the faster memory. Example can be the cache. Now, T1 is the access time to level 1. So we can see very shorter time. And to T2, which is more longer, is access to level 2. As can be seen, for higher percentage of level 1 access, the average total access time is much closer to that of level 1 than of level 2. So in our example here, suppose 95% of the memory access are found in the cache. Let's say H equal to 0.95 or 95%. Then the average time to access the byte can be expressed as, again, the time was 0.1 seconds. So it will be 0.95 times 0.1 second plus 0.05 times 0.1 seconds plus 1 second, which in all, it will give us roughly somewhere around 0.15. So the result is close to the access time of the faster memory. So using the average. So the strategy of using 2 memory levels work in principles, but only if the condition A through D in the preceding list apply. And that was the previous condition here. The cost, capacity, time, and also the frequency of access. Now, next we go to the concept of principle of locality. So the basis for the validation or validity of a condition D is the principle known as locality of reference, or the principles of locality. Here we talk about decreasing frequency of access to the memory by the processor. So during the course of execution of a program, the memory references by the processor tend to cluster. Then both for the instructions and data. Again, they tend to cluster, that's the memory references by the processor tend to cluster for both, again, the data and the instruction. Now, programs typically contain a number of interactive loops and subroutines. So once a loop or subroutine is entered, they are repeated references to small set of instructions. So similarly, operations on tables and arrays involve access to the cluster set. Again, the cluster set data types. Now, over a long period of time now, we can notice that the clusters in use will be changing, but over a short period of time. So the processor, again, is primarily working with phased clusters of memory references. Now, we have 3 forms of memory. The major 3 forms of memory, just going to describe. One thing we know about memory, we have the one that is volatile. Volatile means when the data is, power is off, the data are lost. So we have secondary memory, which also referred to as auxiliary memory. This will be external. It can be external, like a flash drive, hard drive, external hard drive. It's non-volatile because if computer is on and I save my data, if I turn the computer off, the data will still be there, and normally used for store programs and data files. Now we also have the cache memory. Now, the use of the 3 levels express the fact that semiconductor memory comes in variety of types. And we may discuss this more details when we cover memory lectures, and also virtual memory. That's memory management. So cache memory, although we say that cache memory is invisible to the OS, still it interacts with other memory management hardware. So invincible to the OS, but interact with other memory management hardware. Furthermore, many of the principles used in virtual memory schemes, which we are going to discuss in chapter 8 of our course textbook, are also applied to cache memory. So on all instruction cycles, the processor normally accesses memory at least once to fetch the instruction, and often one or more additional times to fetch operands and or store results. So the rate at which the processor can execute instruction is clearly limited by the memory cycle time. That's the time it takes to read one word from or write one word to a memory. So here we're going to explore the principles of locality with a small fast memory, because the processor execution normally is limited by the memory cycle time. So we can see again from the diagram we have, and here we have the CPU. As we said earlier, we can see where the main memory is. So the cache is more faster for the CPU to access. So we say fast, but the CPU to access data or instruction from main memory is very slow. Now we can see our second diagram. We have different, as we said, different levels of caches, or even a register which can be inside the CPU. So it will be more faster. So level 1 will be fastest, level 2 fast, level 3 less fast, then main memory access very slow. So cache memory is intended to provide memory access time approaching that of the fastest memories available. Also at the same time support a large memory size that has the price of less expensive types of semiconductor materials. So we know level 1 cache is more expensive. So we can see the size of the memory or by using the box size. The faster the memory, that means closer to the CPU, the less the capacity, because it's too expensive per bit. So the concept again, it shows in these 2 diagrams here. So there's a relatively large and slow memory together with small, faster cache memory. Almost every computer designs look something like this. As we said, we may even have a register in the CPU, which is also a memory, which again, very close to the CPU. The closer the memory to the CPU, the faster the CPU can access it. So when the processor attempts to read a byte or a word of memory, a check is made to determine if the byte or word is in the cache. If so, the byte or the word is delivered to the processor. If not, a block of main memory consisting of the same face number of bytes is read into the cache, and then the byte or word is delivered to the processor. This is what will take more time. So because of this phenomena of locality of reference, when a block of data is fetched into a cache to satisfy single memory reference, then it's likely that many of the near future memory references will be to the other bytes in the block. So we can see the concept here. And this diagram will illustrate the read operation. You can see the processor again generates the address, RA, read address, RA, receive address, RA, that's the start from the CPU. Then if the word is contained in the cache, it will be delivered to the CPU. If not, then we go deliver, otherwise the block containing the word is loaded to the cache and again delivered to the processor. So we can see the flow diagram here. Start, receive address array from the CPU. Is block containing the array, that's the read address in the cache? Yes. If yes, then we fetch the array word to deliver to the CPU. Then we are done, more quicker. But if no, then we have to access the main memory for the block containing the read address array. Then we allocate a cache slot for the main memory block. So then we load the main memory block into the cache slot, then we deliver it to the CPU. So we have different types of cache, as we saw level 1, level 2, but they're all the same design. Again, the difference is the speed, access time. So if we are designing a cache, these are the elements or the key elements that we have to consider. We should consider the cache size, the block size, the mapping function, and then replacement algorithm, and also the writing policies, policy, the write policy, replacement algorithm, mapping function. So we'll go through each of these. So the cache and the block size. So here we say the cache size will be the small caches have significant impact on performance. As we said earlier, small caches are more close to the CPU, so more faster. Then we have the block size, the unit of data exchange between the cache and also the main memory. So we have already dealt with the issue of cache size. Now it turns out that the reasonable small caches can have a significant impact on performance. And also another size issue is that of the block size, the unit of data exchange between cache and main memory. So as the block size increases from very small to larger size, remember the diagram, the H, which is the hit ratio, will at first increase because of the principles of locality. The high probability that data in the vicinity of the reference word are likely to be referenced in the near future. Now, the next is the mapping function. Here we are going to determine which cache location the block will occupy. There's two constraints affecting this design. Again, when one block is reading, another may have to be replaced. And also the more flexible the mapping function, the more complex is the circuitry required to search the cache. So when a new block of data is read into the cache, the mapping function determines which cache location the block will occupy. And as we said, the two constraints here affect the design of the mapping function. First, when one block is reading, another may have to replace. We would like to do this in such a way as to minimize the probability that we will replace a block that will be needed in the near future. So the more flexible the mapping function, the more scope we have to design a replacement algorithm to maximize the hit ratio. And that will be the next replacement algorithm. And the concept here is that the least recently used algorithm, this is an effective strategy that can replace a block that has been in the cache the longest with no reference to it. So the least recently used will replace that. And also the hardware mechanism are needed to identify the least recently used block. So the replacement algorithm again chooses within the constraint of the mapping function which block to replace when a new block is to be loaded into the cache. So the one that has not been used for a long time, the least used one, will be replaced. Now we also have what we call the write policy. So the write policy normally would dictate when the memory write operation takes place. At one extreme, The writing can occur every time that the block is updated. And at the other extreme, the writing occurs only when the block is replaced. So the writing policy states when the memory writes, it can occur every time the block is updated or can occur when the block is replaced. This will minimize the write operations and also leave the main memory in an obsolete state. So the next is the I/O techniques. And here we say when the processor encounters an instruction relating to input and output, it executes that instruction by issuing a command to the appropriate input-output modules. So there are three techniques that are possible for the input-output operation. That is the program input-output, or if there's an interrupt-driven input-output, or the direct memory address. So again, when the large volumes of data are to be moved, a more efficient technique is required, which is the direct memory address. So this is performed by separate module on the system bus or incorporated into an I/O module. And as we said, when the processor wishes to read or write data, it issues command to the direct memory address module. Yeah, whether a read or write is requested or the address of the I/O device is involved. Also the starting location in memory to read and write, and also the number of words to be read and written. The next is the Symmetric Multiprocessors, SMP. This is again a standalone. It's defined as the standalone computer system with the following characteristics, as we can see. First, there are two or more similar processors of comparable capabilities. Also, these processors share the same main memory, and also the input and output facilities are interconnected by bus or other internal connection scheme, such as the memory access time is approximately the same for each processor. Also, all the processors share access to input and output devices, either through the same channels or through different channels that provide path to the same device. All processors can perform the same function. So that's why we say use the term symmetric. Now, what are the advantages here? Performance. The system with multiple processors, of course, will yield greater performance. It's like you have two people building one house, 10 people building the same size of house. They will be more faster. Even there will be overhead of communication, but still faster. Also, scaling. Vendors can offer a range of products with different prices and performance characteristics. And also availability. The failure of one processor does not halt the system. The other processors can again continue the work. And also the incremental growth. We can add as many processors as we want. We start with 2, next time can make it 3, etc. Increment it. So that's a very good advantage of SMP systems. We also have what we call the multi-core computer. A multi-core computer, also known as the chip multiprocessor. Normally here we combine 2 or more processors, which we call the cores, on a single piece of silicon called a die. Typically, each core consists of all of the components of an independent processor, such as each core will have its own register, its own ALU, which is the arithmetic logic unit, the pipeline hardware, the control units. So each processor have all the possible components elements to perform on its own, including the caches. So in addition, the multi-cores, contemporary multi-core chips also include L2 cache, that's level 2 cache. In some cases, it has level 3 cache also. So again, thank you for these lectures. In these lectures, again, we cover the concept of memory hierarchy and also memory relationships. So as we mentioned, the cost, the capacity, the performance, those are the three main things we need to consider. We have memory that have large capacity, but very slow and is cheaper. Memory that have high performance is very expensive, so the capacity is small. So those are the relationships between the memories. These three characteristics will define the relationship. So for example, memory, cache, and register. Register is the most faster, most expensive. So capacity is always less, as we saw in the pyramid. The next will be the cache, then the main memory. Then from main memory, we have our secondary storage devices, the permanent hard drive, flash drive, etc. So again, wish everybody the best and thank you for your time.